50 or 60 years, mostly in university settings, but we therefore coordinated a little bit, and I think that each of us will take a different perspective, and hopefully the four talks together will give you a real sense of the evolution of this field, as well as the current status, but also of the roots, how this all got started. There we go. My goals for the day then are to discuss a little bit about the state of the art, medical AI. This is part of a trajectory that goes back till the 1960s. Arguably, the field of AI goes back even a little bit farther. I'm going to have to turn off my speaker because I'm hearing myself. Excuse me. How do I do that? I bet I can do it here. So I hope you can hear me now. I'll turn it a little bit. I want to say a little bit about the unique challenges of medicine. They had something to do with the growth of AI in general, because medicine had challenges that many other fields where AI was being experimented with did not encounter as much. And then some of the work in the medical area, therefore, fed back into other areas of application. So we were very much a part of the overall AI history, with a lot of interest in what was happening in the medical areas. And of course, this is a field that has promise, but it also has generated many concerns. And we'll go among the four of us, I think you'll hear a fair amount of discussion about that regarding the adequacy of performance and the implications of the field ethically, and how we prove its value. So there was a quick mention of this John McCarthy conference back at Dartmouth College in 1956. That's when the name artificial intelligence was first introduced. But as Victor pointed out, there was work going on even before that, and many people know Alan Turing and his work and the so-called Turing test, which was really a kind of a early effort to talk about computers and the way in which one could determine if they were intelligent. Many people who have just discovered AI recently think that machine learning is a new topic. But really, machine learning was part of AI right from the beginning, as early as 1959, when Arthur Samuel at IBM Research experimented with trying to get a computer to be able to play, not chess, but checkers, the game of checkers. And he found that the machine he was programming to play this game soon could beat him. He wasn't an expert himself, and he was able to get program running on more than one computer and have it play itself on the other computer. And in this way, with the constant updating of the scoring functions and the like, the computer learned to be great at checkers, probably as good as any human being could be. One thing to remember as we talk about what was happening in the 1960s and 1970s is that this is before personal computers, before the robust internet of today, before we had electronic health records and medical data in digital form. And so in spite of that, there was an awful lot going on that used large computers, because all computers were large in those days, to study areas such as machine learning. Neural networks went along with machine learning, originally called perceptrons. The understanding of natural language and proper responses to natural language. Understanding speech, which we take for granted today when we talk to our phones to get them to do things for us. But that was all very futuristic at the time and was an area of research. And we in medicine tended to focus a lot on the simulation of human problem solving and how human beings solve difficult problems in medicine. There were even some early work in robotics in that era. And so we saw the emergence of applications of artificial intelligence in medicine. They were all experimental. They tended to encode knowledge that was obtained from expert clinicians. And as a result, these kinds of systems were often called expert systems. If you go back to a textbook from the early 1980s, this is how I was interested to see that AI was defined at the time. Fundamentally, the idea of getting computers to do things that make human beings seem intelligent, but with a focus on reasoning symbolically, not mathematically per se, to acquire knowledge and then to apply that knowledge in appropriate settings and to manipulate and communicate what we would call ideas. I think today you'd see a little bit more emphasis on the machine learning end of the spectrum, which is less about knowledge encoding, but rather knowledge derivation from huge amounts of data. Many people would cite these as the four best known AI programs in medicine in the 1970s when I got into this field, when all four of us were in this field, who will be speaking today. The internist program at the University of Pittsburgh, the CASNet program at Rutgers University, our work at Stanford University in a program called MYCIN, and the PIP program that Pete Solovitz and others were involved with at MIT and Tufts University. And many of the techniques developed by these programs in medicine, as I suggested, were then broadly adopted or experimented with outside of medicine in other domains. So Kaz Kulikowski will talk to you and will no doubt mention CASNet. Pete Solovitz is also going to be speaking after me and can refer back to this work at MIT and Tufts. And I now will talk a little bit about MYCIN, just to use it as an example of what was happening in the 1970s and how that led into the work of the 80s and 90s. This was my PhD dissertation at Stanford. I was an MD and a PhD student at the time. The topic that we were working on was to see if we could understand how you could give expert advice about how to treat a patient with a serious infection with antibiotics, even before you knew the results of the cultures that were being done on that patient. We needed to encode the expert knowledge necessary to analyze such cases. There was a core engine that could be used to give advice based on that medical knowledge, which was stored in rules. And there was an explanatory capability that was built into the system. And I'll give you some examples of that so you get a feel for what I mean. And the dissertation came out as a book, which of course is long out of print, but I have a copy anybody who wants to see can get access to on my personal website. The knowledge was encoded, as I said, in rules using a language called Lisp. This is an example of a rule. You can probably almost figure out what it says, but of course this would not be a great way to communicate with physicians who were using the program. So it turns out that because it was a fixed syntax, we could use programming to convert this into English. If we needed to use it in an explanation, we would actually, of course, communicate with an English-speaking clinician using these English versions of the rules that were generated from the encoded version. This allowed us to work on problems of explanation, which seemed to us intuitively to be an important capability, that if you were going to get advice from a computer and you were a clinician dealing with real patients and their lives and illnesses, you certainly wanted to have enough insight into what the computer was recommending that you could make a wise decision. So back in about 1981, we did a detailed study to try to understand what physicians would demand of a computer program that they were going to use to get advice. And we had a big meeting. We had many physicians, over 200, fill out forms and say, these are the demands, the most important capabilities that I could imagine. It was all written up in an article back in 1981 on physician attitudes regarding computer-based clinical consultation systems. And this is a list of some of the top ranked demands that the physicians identify that they wanted to be sure such a computer would be able to do before they would use that program. And I would just point out the absolute top one was they need to be able to explain their diagnostic and treatment decisions to physician users. They should display an understanding of their own medical knowledge. They should display common sense. They should simulate physicians' thought processes. This seems to be a plea for many of the things we were emphasizing in the work on AI in medical consultation. So an example is that if you were being, this was, remember, all being done in text. There were no imaging yet or no programs or terminals that could draw pictures. So it was all a text-oriented interaction. And if you were being asked a question during this interaction with the program, highlighted here in red, why are you asking me that? Rather than answer the question, you could say, why do you want to know this? And it would give back in the form of the rule currently under consideration, a translated version saying that, you know, if I can find this out, this is what I can conclude. So it interpreted the question as, why do you want to know whether a significant number of organisms has been obtained? And of course it says, well, it's important because I'm trying to decide if there's a therapeutically significant disease. And so like any persistent child who keeps saying why to every answer, you can say why again, in which case you'd be saying, why do you need to know if there's therapeutically significant disease associated with the occurrence of this organism? And if you did that, it would give yet another rule that was under consideration in a chained fashion with the first one. These kinds of explanations did provide insight into the way that the program was thinking about the problem, if you will. So a common perception or perspective at the time was that we could get clinicians to use these kinds of systems if the programs could be shown to function at the level of experts. That meant we needed to study and simulate how experts in the field reasoned, and then use expert performance to benchmark the system. And that's really why this expert systems nomenclature or description of these systems came up. But if you're going to do this, you have to show that the program has expert performance, similar to what a physician could do. So formal evaluations were crucial. And in the case of MYCIN, it took us a couple of years, but finally in 1979, we were able to publish in the Journal of the American Medical Association a blinded evaluation by infectious disease experts comparing other experts and how they handled cases with how MYCIN handled the same cases. It was a positive study and I think raised a lot of eyebrows who couldn't imagine that computers were doing these kinds of problems at the time. In fact, the AI and medicine community spent a lot of time trying to understand how human beings reason. Cognitive science became a big part of this aspect of our artificial intelligence effort. And there were whole books on the subject that were being written and studies that were done to try to gain insights into the human being's approach to similar problems. Well, despite all this enthusiasm, things go a little slow in this hard and difficult field. There was disappointment that applied artificial intelligence, which had a lot of attention in the press, had somehow or other not seemed to live up to the predictions for impact by the late 1980s. There was a claim that the field had been oversold and that there was too much hype. And this led to a kind of avoidance of the use of the term, disappointment, and what has been known in retrospect as AI winter. Well, AI winter was a period, actually there was a little AI winter in the late 70s before medicine was really as involved. But the other one was this one up here in the late 80s and early 90s, when people literally didn't want to say they were doing AI for fear that they couldn't get support to do the kind of work that they wanted to do. Yet by 1993, things began to take off again, and I think it's fair to say that there hasn't been another AI winter yet. You may want to hear from us whether we think that could happen in the future, but right now, I think the exploding interest does not seem to be slowing down much. So what was it that made AI take off? Well, first, there was a huge evolution in the technology itself. Networking, the internet came into play, and suddenly we were able to pool data and collect data from multiple sources. Personal computers came in the early 80s, graphical workstations, so we began to get the ability to do graphics on computer screens and use them in a variety of interesting ways in these kinds of interactive systems. Suddenly memory became cheap, high density. You could store a whole lot. That enabled us to have mobile phones that store much more information than we could get in even relatively big computers in the early days. And this is an exponential curve showing the growth, the so-called Moore's law of computer processing power, and also a big impact from graphical processors, which had an ability for us to process much more quickly than before. In addition to the technology evolving, there was an evolution in the methods. Suddenly we were able to put together huge databases and develop methods for dealing with very large data sets. As I indicated earlier, machine learning finally had a reasonable basis, and it grew substantially starting in the 1990s and really took off in after 2000. A field of data science, which began to look at the mathematical and statistical methods that merged with data that had been stored. Cloud computing, a lot of processing power off on the internet, not just on your own computer, and storage of data and getting computing done elsewhere than on your own machine. Work in structuring terminology for fields, which is crucial in medicine. The speech understanding really blossomed during that period. We saw machine learning evolve into deep learning, which I think was the real revolution that recently actually won the Nobel Prize for those innovations. And today we see these large language models that were inconceivable when we were first working in this field. And then medical applications evolved, a broadening of the uses of AI in medicine, electronic health records, of course, which were crucial to much of what went on, applications spreading off into biology and computational biology and public health, imaging suddenly moving from film to being digital, and it became yet another kind of data element that could be studied using AI methods, and now, of course, medical chatbots. So the transition occurred in the United States, at least, pretty much during the decade that followed the start of the 21st century. This is the way medical records were stored, certainly when I was first studying medicine. But they largely have disappeared and did gradually over that decade, so that we had electronic health records. They resulted in large amounts of digital patient data, including images and new capabilities due to the deep learning methods, and therefore huge opportunities to learn from literally millions of cases and learn new things that might not even be in the heads of experts. So I like to close with just a brief summary of, I think, some key things to think about what it takes to be sure that you have acceptable systems that will integrate into the workflow in which clinicians work. One is this notion that black boxes are unacceptable. This was the need for explanation. And to this day, I think many of us feel that at least for consultation style uses of of AI systems in medicine, you really need to be able to provide some insight into the basis for the decisions. We need to be respectful. The clinicians are key players in this. And drawings like this that suggest that the computer is becoming the doctor really aren't very helpful in this regard. Even worse are ones like this that really personify the doctor in a robotic kind of way. But instead, most of us are very much arguing the case that what is possible with the best of these kinds of systems is to enhance the ability of the clinician by adding a computer in the mix. But that's the strength, is in the combination of physician aided by computational tools. And recently, there's been an effort to emphasize that implication is that the computer alone can't do it either. It needs that clinician's unique perspective. And the final set, they have to be efficient. If they're not, if they disrupt workflow, people won't use them. They have to be intuitive, simple to learn. You can't require a 4-hour course from a clinician before it can use one of these tools. They have to reflect an understanding of the pertinent domain, the likely needs of the users. As soon as the computer asks a question which seems really off base, it raises questions on the part of the users, and it has to have rigorous peer-reviewed scientific evidence. This need for formal studies that demonstrate the safety, the validity, the reproducibility, the usability, and the reliability of the systems. So I close with these thoughts about future directions. I think we all have to be asking how we can best leverage how human beings and especially acknowledged experts solve the problem. It may not be the identical way that experts do, but we may get insights from studying what they do that will enable us to get even better systems fielded. Recognize that the promulgation and acceptance of medical AI solutions is going to depend on much more than just their decision-making or analytic performance. This transparency issue, for example, leads to trust, and there are many other aspects that depend on a collaborative role for physicians and their expertise while addressing things like usability and workflow, patient variability, avoidance of bias, and the ethical performance of these programs. I think the future is bright, but we're still in midstream. There's still lots more to do, and I hope that the talks today will inspire everyone to get involved and promote that idea. So thank you. I appreciate the time.